Alright, in this video we're going to look at linear ODEs. This is going to be linear ODEs of order 1, because we do also have linear ODEs of order, say, 2, which we're going to look at in another video. Actually, it's going to be a set of videos for that one. Alright, so a first order ODE, is said to be linear if it can be written in the form dy dx y prime plus y times function of x p equal another function of xq. So let's call this equation number 1. So just for emphasis, so the functions p and q are functions of x only. Functions of x only. So casting this equation, so let's just write casting 1 into the form, so one write it in the form m dx plus n dy. So this one becomes dy into y p of x minus q of x dx equal to 0. Okay, so if we write it in this form, so this is going to be our m, and which means our n is 1 here. Okay, so if we do that, then we see that like I said, n is 1, m is y, p of x minus q of x. Then my minus nx all over n is just p of x. Okay, so if you check our video on integrating factors 1, then you will notice that we established there that since this is a function of x only, okay, since this is a function of x only, then the integrating factor of 1, integrating factor of equation 1 there, let's call this one 2, let's call this one 3. So integration factor of 1 is going to be given by mu of x is equal to the exponential of the integral of p of x. Okay, let's call this one equation number 4. Notice that so if we differentiate this equation number 4, d nu dx so it's going to be d dx of the exponential of the integral of that. Well, the derivative of an exponential is the same exponential times the derivative of the exponent. The exponent here is the integral of p. So derivative of the integral of p is just p. So this is going to be p of x times the exponential of the integral of p of x. So now notice that this is just mu. So we can actually write this as p of x times mu of x. Okay. So what this is saying is that mu prime is mu times p. Okay. So what I want to do now is we're going to go back to equation 1. So if we start with y prime plus, remember we've got y p is equals to q of x. Okay. If I multiply everything by mu, which is our integrating factor, then we're going to have mu y prime plus, let's write it as y mu times p mu times q. And then from here, mu p is just mu prime. So this here is mu prime. So I can write this as mu y prime plus y mu prime. Okay. Now notice this is just the product rule expansion of this derivative. So if we differentiate y mu prime, if differentiate y mu by the product rule, it's going to give us mu y prime plus y mu prime. Okay. But then the good thing is that this is now already exact in terms of we can integrate it straight away. Okay. So, and that's what we're going to, that's the whole point of the integrating factor. So we're now going to look at some examples. All right, before we go into examples, I'm going to label this equation 5 because it's going to be so very important when we work through the examples. All right, so in these examples, we have got ODEs stroke IVPs. In part B and C, we've got an initial condition, so these two are IVPs. some of the equation may be given in this form, or it may be given in the form m dx, m dx plus n dy equal to 0. Okay, so in each case we will want to put it in this form. Okay, by the way, if the ODE is given in this form, then there are two ways of seeing two conditions if it's linear. First of all, the y must not multiply the dy term. So like here in the dy, in the m term there is no y, and then in the n term, then in the m term the y must just be to the power of 1. Then your equation is linear. So for instance, this one straight away you can see it's going to be nonlinear because the y squared and the y are multiplying the dy. Okay, so we'll see how we handle this one when we get to part D. These ones are in the form of equation 1. So these ones, it's very clear that they're linear because y occurs to the power 1. In each of these terms, it's multiplied by a function of x, and then that's going to be our q, which is the term on the right hand side. Okay, so let's get on with part A. So in part A, we've got 2y prime plus y is equals to 2x minus 4. So the first thing, if we want it in this form, the coefficient of y prime must be 1. So we divide everything by 2, going to be y prime plus 1/2 is equals to x minus 2. Then the integrating factor mu is going to be e to the power of integral of p. P is 1/2, so this is going to be e to the power x over 2. Okay, and so if we multiply this by this, straight away we're going to go to the form 5, which is y times the integrating factor. Okay, so multiplying by mu gives, so straight away we're going to go to the form ye to the power x over 2 prime, okay, or ddx. Maybe just for now, let me write it in the form ddx of that. Then on the right hand side, going to have x minus 2 e to the power x over 2. So that's just this form here. And then on the left hand side, we've got an exact derivative. So this we can integrate. So if you like, if we take dx to the other side, so we've got d of y e to the x over 2 equal x minus 2 dx. Then if we integrate on both sides, the left hand side, which is going to have y times mu. Okay, then this side going to have to use tabular integration to evaluate that one, so let's just do that here. So we've got x minus 2, derivative of that is 1, derivative of 1 is 0. Here I've got e to the power x on 2. So these are the integrals of e to the x on 2. This is the integral of this one, and this is the integral of this one. And then we match them. The first pair is going to be plus. The second pair is going to be minus. Okay, so if we do that on this right hand side, we're going to have 2x minus 4 minus 4e to the x over 2 plus a constant. Okay, then if we divide everything by e to the x on 2, which we can because e is never 0, so our solution is going to be 2x minus 8, okay, plus the constant times e to the negative x on 2. So that's going to be our final solution. Right, so that's A. Now go to B. B, we've got y prime minus 2xy is equal to x. When x is 0, y is negative 1. This one is already in the standard form, if we're going to call that equation 1 the standard form. So straight away p is negative 2x. So all we need to do is just to work out the integrating factor. So integral of negative 2x, this is going to be e to the minus x squared. Okay, then multiplying the ODE gives, so straight away the left hand side is always going to be y times the integrating factor derivative of, okay, and then the right hand side of course is going to be q times that. And then again, if we integrate here, the left hand side is just going to be the quantity inside the square bracket. The right hand side is going to be the integral of this. Okay, that integral we can evaluate using u substitution. If you are not up to speed with that, do check our video on the u substitution method of integrating. But this is going to give us negative 1/2 e to the minus x squared plus a constant. Okay, now if we bring in the initial condition, so the initial condition says when x is 0, y is negative 1. Okay, so on the left hand side we're going to have negative 1 times 1, because if you plug in x is 0 here, this becomes 1. Right hand side is going to be k minus half. Okay, so this is going to give us k is equal to negative half. So that's going to plug in there. And that is going to be y e to the minus x squared equal to minus half e to the minus x squared. Then if we make y the subject of the formula here, it's going to be minus 1/2 1 plus e to the x squared. So that's going to be our final solution. Okay, then we're now going to go to part C. So in part C we have got y prime minus 2y is equal to sine x when x is 0, y is equal to 2. Okay, so again this is in the form of equation 1. So p is -2, so the integrating factor is simply going to be e to the integral of -2 dx, going to be e to the minus 2x. So so if multiplying gives, so remember the left hand side we're always going to have y times the derivative of y times the integrating factor, and then on the right hand side that is what we are going to have. Then if we integrate on both sides, the left hand side is going to be y e to the minus 2x. This side we're going to have the integral of e to the minus 2x times sine x dx. Now this integral, if you check our video on integration by parts, you'll find that we suggest that if it's an integral of an exponential times a trigonometric function, sine or cosine, then what you do is you integrate by parts twice and then you turn it inside out. The alternative method is to use the complex numbers approach. We are going to use that one in this video here. So just here I'm going to take a small detour and evaluate this. It's going to take a bit of a while. So if we use the complex approach, what we do is we write sine as the imaginary part of e to the ix. So e to the ix is cosine x plus I sine x. So if you take the real part of this, just picks out the cosine. If you take the imaginary part of it, then it just picks out the sine. So the imaginary part of e to the ix is just sine x. So if you take the imaginary part of this, it's just going to be e to the minus 2x sine x. All right, so then so this is going to be the imaginary part of the integral of e to the, combine the exponentials, that is going to be e to the I minus 2x, and then so we can integrate that. The integral of e to the ax is e to the ax over a. So this here is going to be e to the I minus 2x divided by I minus 2. Remember, I is just a constant, and then plus k. Then we need to extract the imaginary part of that. But the e to the minus 2x we can factor out, because that one is a real number. So it's just going to go through that imaginary operator. So this is going to be e to the ix over I minus 2. Okay. In order for us to extract the imaginary part of that, we're going to write e to the ix as cosine x plus I sine x, as I already mentioned, divided by that. Then what we need to do is to remove the I from the denominator. And so we do that by multiplying both numerator and denominator by the complex conjugate of the denominator. Okay. Then when we do that, in the numerator, we're just going to have 1 squared plus 2 squared, which is 5. That's the denominator. In the numerator, what I'm going to do is I'm going to factor out the negative from these two terms here. So I'll put the negative there outside. Then that term is just going to be 2 plus I. Then multiply this by cos x plus I sine x. Remember, in the denominator we said that is going to be 5. Okay, then multiply out there. So this is going to be imaginary part of. I'm going to start with the real terms first. So 2 times cos x is going to be real. Then I times I sine x is going to be real because I squared is negative. And then the imaginary parts, 2 times I sine x is going to be I into 2 sine x. Then I times cos x is just going to be cosine x. I'm going to bring the 5 outside here. And then this is plus k. And then from here, the imaginary operator is just going to pick out this term here. So that means our integral is negative e to the 2x all over 5 times 2 sine x plus cos x plus k. Okay, right, so then we're going to take that and plug it in here. Okay, so we're going to have, therefore we have got ye to the minus 2x is equal to negative e over minus 2x over 5 2 sine x plus cos x plus k. What we can do is apply that boundary condition at this point. The initial condition, so when x is 0, y is 2. So that means the left hand side is going to be 2. This term is going to be minus 1 over 5, 0 plus 1 here, plus k, because sine 0 is 0, cosine 0 is 1. And then from here, it tells us that k is going to be 11 over 5, which is 2 plus 1/5. Yeah, then if we plug that in here and make y the subject of the formula, then we're going to have that y is 1 over 5 into 11e. 11e to the 2x minus 2 sine x minus cosine x, and so that is going to be our particular solution. All right, so that was a bit involving. So that was part C. We're now going to go to part D. In part D, we have 1 plus y dx minus xy plus y squared dy is equal to 0. We already noted that this equation is not linear. The ODE is non-linear. However, if we take x as the dependent variable, take x as the dependent variable, then the equation becomes, let's say we have dx dy, okay, so taking x as a dependent variable, minus yx over 1 plus y is equal to y squared over 1 plus y. Okay, this equation is linear in x because x is to the power 1 here, that's the derivative of x. That coefficient is a function of y, that's a function of y exclusively. Okay, so we can integrate it using the same methods. So yeah, so this is linear, let's say, which is linear in x. So the integrating factor is going to be the exponential of the integral of minus y over 1 plus y dy. This function is an improper rational function. If we divide first, we get minus 1 and the remainder is going to be 1, so that it's going to look like that, and so that's going to be the exponential of negative y plus ln 1 plus y. So this just works out to 1 plus y e to the minus y. So if we multiply this equation by that, the left hand side, I'll multiply ODE by nu. So the left hand side is just going to be dy this time, because we've just made y the independent variable. So it's going to be x into 1 plus ye to the minus that, and the right hand side is just going to be that, so it's going to be y squared e to the minus y, e to the minus y. And so if we integrate, the left hand side is going to be that, the right hand side is just going to be the integral of this, which we can evaluate using tabular integration. All right, so integrating this right hand side gives us negative y squared plus 2y plus 2 that is going to be done using tabular integration or integration by parts twice. Okay, then if we regroup this, multiply everything by e to the y, and group the terms, going to be y squared plus x into x plus 2 into y plus 1 is equal to ke to the y. All right, okay, now let's go back to the set of examples. Okay, now we're going to give you a chance to redo some of these. Okay, B, we have worked it out as a linear equation, but this can also be integrated using another approach. I'm just going to list the other options here that we've covered so far. We've covered separable equations, we've covered homogeneous equations, we've covered exact equations, and then we've covered equations that can be evaluated using integrating factors, and then now we've covered linear. We've just evaluated this as a linear ODE. Now what I'm saying to you is this equation can also be classified and hence integrated as one of these others. So just do your analysis and see which other one it falls under and work out the equation using that other method. Same thing with this one. Okay, so here this one we wrote it as well, x as a dependent variable, and then it was linear, but it can also be evaluated using one of these other classifications. Okay, and then also have a go at E. So that's three problems for you. So if you just pause the video and then have a go at those, then when you continue the video, then you'll find our solutions. All right, we're now going to scroll down to look at an alternative method to work out part B, and an alternative method to work out part D, and well, just a method to work out part E and a method. Okay, so for part B, what you hopefully will have found out is that part B is separable. So you can see there is an x term this side, and then next term. So if we bring this to the side, we can factorize x, and then we bring the y terms to the one side, and then integrating this gives us that one gives us x squared over 2. If we take exponentials on both sides, that's what we're going to get. Maybe let me just put a 2 here, because we multiplied out by 2 first, and then e to the 2k is a constant. Let's call it a. And then if we remove the absolute values, means 2y plus 1 is plus or minus a e to the x squared. Then when we apply the condition, we're going to have to treat the two cases differently. If you take the plus case, gives us a is minus 1. So that means it's going to be minus 1 there. If you take the negative case, gives us a is 1. So that means this becomes negative. So in both cases, we have a negative here. So then you rearrange, and this is the solution you find. I think you will recognize this as the same solution we found using the linear approach. Okay, and this one, it turns out that when you do this combination here, it's going to be a function of y only. Well, it's a constant, but so that's as good as a function of y. So that means we can find an integrating factor of this type. And then if you multiply the equation by that, this should now be exact. Okay, you can actually confirm. So if we so it's going to be a function which says that its derivative with respect to x is m. Integrate that with respect to x, you get this, and then we differentiate. All right, and so differentiating this with respect to y gives us this, but if you open brackets here, this term is going to cancel out with that term, so we're just going to have this. If we compare this with fy, then you can see that this term is the same as this one. So phi prime must be equal to this one. And then if we integrate this using tabular integration, we get that. We'll plug it in there. This can be rearranged to look like this, which is pretty much similar to what we got using the linear approach. All right, for D, if we just write it in the form of equation 1, then that's our P. Integrating that gives us this as an integrating factor. And then if you multiply the ODE, this one, by the integrating factor, this is what we have. Integrate on both sides and make y the subject of the solution. So it gives us that final solution. Thank you for watching. Hopefully find these useful. Please do subscribe so that you will get notified of whenever we post new material.